A flat steel box would actually be weaker than a corrugated one, even if you made it from thicker steel. That's the core of why every shipping container on Earth has those wavy walls, and it's a geometry trick that goes back to Victorian-era train cars. Here's what you'll actually learn. Why corrugation multiplies stiffness without adding weight. How container walls handle forces you'd never think about. What happened when engineers tried to skip the ridges, and where the same geometry shows up in places that have nothing to do with shipping. Most people assume the corrugated walls are just a manufacturing quirk, something to do with how steel is stamped at scale, or maybe a way to make the panels look grippy for branding. Neither is true. The ridges are doing serious structural work, and the physics behind them has been understood since at least the 1880s, when railway engineers were trying to build lighter freight cars without sacrificing load capacity. The insight is simple once you see it. A flat panel resists bending in only one plane. A corrugated panel resists bending in both planes, and it does it with almost no added material. The same amount of steel, shaped differently, becomes dramatically harder to deform. Here's the precise mechanism. When you press on a flat sheet of steel, the material near the neutral axis, the center line of the sheet's thickness, carries almost no stress. The load is handled by the thin outer surfaces, so most of your steel is doing very little. Now corrugate that same sheet. You've turned a thin, flat profile into a series of connected arches and troughs. The effective depth of the section, meaning the distance between the outermost fibers in bending, increases dramatically. In structural engineering, this is called the second moment of area, sometimes called the area moment of inertia. It scales with the cube of depth. Double the effective depth, and you get 8 times the resistance to bending. A corrugated panel with a ridge height of around 50 millimeters, which is roughly what you see on a standard ISO shipping container, can have an effective bending stiffness dozens of times greater than a flat panel of identical steel weight. That's not a marginal improvement. That's a different category of structural performance. Core 10 steel, which most containers use, is already about 30% stronger than mild steel, but the corrugation is doing far more work than the alloy choice. Now here's the interesting counterpoint. Flat wall containers do exist. They're called curtain-siders, and they use a tarpaulin or fabric wall stretched over a rigid frame instead of structural steel panels. They're popular in European road freight where you need to load from the side with a forklift. The problem is that the frame has to be much heavier and more complex to compensate for the missing wall rigidity. You're essentially adding steel back in the form of vertical posts and horizontal rails. The total weight savings over a corrugated steel container is small, and the curtain-sider can't be stacked 9 high on a container ship the way a standard ISO box can. Stack loading on a container ship can put 90 metric tons of compressive force on the corner posts of a bottom-tier box. The walls contribute to distributing that load. Remove the structural wall and you have to engineer around that absence everywhere else, which gets expensive fast. There's a deeper reason the corrugation pattern runs vertically on most containers, not horizontally. Horizontal ridges would stiffen the wall against vertical loads, like the stacking forces we just described. But they'd make it terrible at resisting the racking force, which is the shear force that tries to make a rectangular box lean into a parallelogram. If you've ever watched a container ship in rough seas, or seen footage of a train rounding a curve, the lateral forces trying to distort the container's shape are constant. Vertical corrugation creates a wall that resists racking because each fold acts like a mini column bracing against lateral movement. This is why the ISO 668 standard, which governs container geometry globally, essentially locked in the vertically corrugated wall as the default. It handles the full set of loads, stacking, racking, and internal pressure from cargo shifting without requiring extra framing. The failure case worth knowing about came from early container shipping in the late 1950s and 1960s, when some manufacturers experimented with shallower corrugations to make containers easier to stack on ships with slightly uneven decking. The shallower the ridge, the lower the effective depth, the lower the bending stiffness. Several of these containers developed wall buckling under heavy loads, where the steel panels would permanently deform inward under the weight of stacked cargo pressing on the roof. A buckled wall doesn't recover. The container becomes unusable, and in a stacked configuration, one failed box can compromise the structural integrity of the stack above it. The industry standardized on a minimum corrugation depth not because of bureaucratic caution, but because people learned the hard way what happens when you shave too much off the ridge height. This same logic shows up in places that have nothing to do with freight. Corrugated cardboard boxes use an identical principle, a fluted inner layer glued between two flat liners, and the result is a material that's roughly 30 times stiffer than flat cardboard of equivalent weight. Corrugated roofing sheets in construction, those galvanized panels on farm buildings and industrial sheds, use the same geometry to span long distances between purlins without needing heavy intermediate supports. Even aircraft fuselages use a version of this, with internal frames and stringers that corrugate the load path through the skin. The Romans built barrel vaults for the same reason. Curved geometry distributes force in a way flat geometry simply can't match. The corrugated shipping container wall is a compressed lesson in structural geometry. More depth equals exponentially more stiffness. And depth is free if you're willing to shape the material instead of just thickening it. Every time you see one of those ridged steel boxes stacked 8 high in a port, that's the geometry doing the work, not brute material strength. If this is your kind of thing, the why behind the everyday, Object Theory drops new ones Monday, Wednesday, and Friday.